So, welcome to all. This is the I am Dr. Diptiranjan Patnaik, working as assistant professor in GL Bajaj Institute of Technology and Management, Greater Noida. Today we will see the match filter, and the previous lecture we have already read about the optimum filter, which is used to extract the signal from a noisy, extract the desired signal from the noisy environment. Now we will see what is the match filter, and the match filter is nothing but the match filter is nothing but a optimum filter when the your noise follows the wide Gaussian noise, and this the purpose of this filter is to increase the SNR and decrease the probability of error. So, the mesh filter, this is the proper definition. The mesh filter is the optimal linear filter. One second. The optimal linear filter for maximizing the signal to noise ratio in the presence of additive stochastic noise or additive wide Gaussian noise. So, if a filter generates an output to maximize the output peak power ratio to mean noise power within its frequency response, then it is called match filter. This is the on another type of definition. So, both are equal. So, in telecommunications, it is the optimal linear filter used to increase the SNR. So, to increase the SNR, we are using the optimal linear filters in the existence of or additive stochastic noise. Okay. So, these type of filters are generally used in radar. Where is the application of match filter? This is your mainly used in radar, where a known signal is transmitted and the reflected signal can be compared with the transmitted signal. If the both signals are equal, then it's a okay, we can say that these two both signals are matched. So, this is the basically this is the basic block diagram of a match filter. This is your signal, okay, and this is your, let us say this is your noise. So, this signal noise are added, and it passed through a linear time invariant filter, that is LTI system, which has a impulse response h of t, and it gives a output as y of t, and after that we will sample this y of t at the interval t equal to at every interval of t equal to capital T, that is we will get y of t. After that, this y of t we will see, and we will apply some decision rules, or this is the decision device. It has to pass through this decision device, and then it will select it will decide whether it is 0 or 1 or whatever the according to the decision rule, it will give the output. So, this is the match filter. So, it has the impulse response h of t, in terms of frequency response, this is h of f. So, we have signal input signal SI of t plus NI of t, that is noise. This is the SI of t plus N of t, this is the SIT plus NIT. Okay. Now, it is passed through a match filter. In the match filter output, we have S naught t plus N naught t, and after that I will sample this y of t at every t interval, that is capital T. So, y of t is your capital Y of t and S naught of t and plus N naught of t. So, we know that S naught t, this is the in the absence of noise, this is S naught of t, this is Si of t, this is H of t. So, what is the relation between these three? So, S naught t is nothing but the Si of t convolution H of t, because it is in time domain. Okay. So, in frequency domain, it is nothing but just normal multiplication of input signal in frequency domain and multiplied by the transfer function in the frequency domain. So, S naught of t, how could I find this S naught of t from the frequency domain? So I can find this like this, S naught of t equal to, I have given the S naught of f multiplied by your e to the j 2 pi f t, that is inverse Fourier transform. So I will get the, from frequency domain I am getting the time domain signal. So your S naught of t equal to your S naught f is nothing but your this much SI of multiplied by H of, just put this SI of multiplied by H of in this place. So I will get SI of f multiplied by H of f into e to the power j 2 pi f t dt. So now I want to find out the S naught of t square equal to, why I am trying to find out this S naught of t square, because we already seen in the previous lecture that how the probability that SNR is depending upon the S naught of t and sigma square. Okay. So S naught of t square equal to how much? This is the mode square. This is the mode square. So S naught of t square equal to SIF multiplied by H of f, and I can write this at the t. I can, if I will sample at capital T, that is, this is the sample, I can write this as simply like, instead of small t I will write as a capital T. Okay. So this was the signal. Now we can expand this noise signal. So noise signal, to expand this noise signal, I have to know the what is the relation between the input noise power spectral density, output noise power spectral density, because noise is power. That's why we are calculating, or we are discussing like power. So we have to consider as a power spectral density. So now we can expand noise like above. If input PhD of noise is Gn of f, output PhD of noise, that is Gn naught of f, what is the relation between the input and output power spectral density? This is the Gn naught of f equal to h square time of f multiplied by Gn of f, that is your h square of f, your transfer function in the frequency domain. So Gn f is your input power spectral density and Gn naught f is your output power spectral density. Now we will write this PhD in terms of power. This is because we will need this for calculating the noise power. Okay. So the variance of Gaussian is nothing but the noise power. I have already same thing I have already told you in the optimum filter. So the for a Gaussian noise, the variance is nothing but is the noise power. So the relation between the noise power and the power spectral density are related as noise power equal to integration of power spectral density. That is, power spectral density is nothing but the some power is distributed some in some area. So I have to, if I want to find out this what is the exact power, then I have to integrate, that is, I have to calculate the power of this distributed areas. So your sigma square, that is noise power, equal to integration of your power spectral density. Okay. So J naught f equal to nothing but your h square of f multiplied by your Gn of f. This is we have already seen this relation. Okay. So your gamma square, that is noise SNR, is nothing but your s square of t divided by sigma square. We can see that why I have calculated s square of t. Okay. This is your s square of t and this is your sigma square. So here also we are using Schwarz inequality to find out this expression. So we know that the inequality equation is integration of x of f multiplied by y of f df square divided by integration of x of f df square, less it is bounded by your y of f, integration of y of f df whole square, mode square. So this the okay. So s naught of t square of t by sigma square is bounded by, okay, this will be bounded by your what how it is bounded? It is bounded by how much? This is SI of square into df multiplied by h of f square df divided by your h of f square into gn of f df. Okay. So, you can see that when the noise is wide Gaussian noise, then the PST is given by your n naught by 2. This is the important point. Okay. So, for wide Gaussian noise, your gn of f is nothing but the n naught divided by 2. Okay. Therefore, so s naught of square divided by 2 sigma square is nothing but less than equal to how much? Your integration of si of f square df multiplied by h of square, and this gnf is nothing but your n naught by 2, and this is the integration part. So, we have both numerator and denominator, we have same terms, so it is cancelled out. Now, we have s naught square t divided by sigma square is less than equal to your this much of term divided by n naught 2. So, I can write this as 2 by n naught multiplied by minus infinite to infinite si of f square multiplied df. This is nothing but your SNR of the mass filter. So, we can see that this SNR depends on the only in the input signal. Okay. This SNR depends only on the input signal, and this is not depending on the noise. Okay. So, it is the this is the very good sign. Now, we can find out what is the energy of the signal. So, energy of the signal is nothing but the integration of minus infinite to infinite si of t square dt. So, I can write I can also write the integration minus infinite to infinite in the frequency domain also si of f square df. So, s naught to s naught of t square divided by sigma square, it is bounded by 2 times, okay, 2 times, that is n naught by 2, that it goes like this, 2 times energy of the signal divided by n naught. So, I can write what is the maximum value of this is equal to 2 this is less than or equal to. So, if equal to, then it would be maximum. Okay. So, 2 energy of signal divided by n naught, this is for the mass filter in terms of energy. So, same for equal sign, we are using the Kraft inequality, that is y of f equal to k times x star of f, with k is an arbitrary constant. So, your h of f e to the j 2 pi f t equal to x star f is nothing but a si star f f. So, we can write now the transfer function of the mass filter is h of f equal to k times si star of f multiplied by this, if it will go this side, it is minus j 2 pi f t. Okay. Now, I can find out the impulse response. So, this is your impulse response. So, impulse response in time domain. How can I get the impulse response in time domain? I have to inverse Fourier transform, that is it is given as h of f, that is in frequency domain. So, integrating this h of f or using I f t, I will get h of t. So, I know that what is h of f. So, this is the h of f, this is the k times si star f f into e to the minus j 2 pi f t. So, this is the k times this much, this is the e to the j 2 pi f t. So, your k is constant, so it is coming to outside. Now, minus infinite to infinite si of f f star of f e to the minus j 2 pi f, your I can write t minus capital T, and it is minus. Okay. So, df. To realize any filter, the response of the filter should be real. So, as if I am calculating h star of t, that is also equal to h of t. So, now I can calculate the h star of t. H star of t, what will happen? So, k times si of t star is star of star, that is your normal si of f, and this one is what is the star of e to the power complex conjugate of e to the minus j 2 pi f t, that is your plus e to the j 2 pi f multiply t minus t df. So, it is your k times, this is your the shifting property, using the shifting property si of t minus t, which is nothing but your again h of t. So, h of t, your h of t equal to k times si of t minus t. So, your input signal is just time shifted. Okay, your input signal is some only for time shifted. Okay. So, this is your match filter, this is x of t input, y of t is output, h of t is the impulse response. So, y of t equal to x of t multiplied by h of t, but h of t, what is the x of t, h of t? This is the h of t is the k times si of t minus t, or you can write the if k equal to 1, that is si of t minus t. So, here that is instead of si of t, I am writing here x of t, generalize x of t minus t. So, this is your y of t equal to x of t convolution x of t minus t, that is similarity we are seeing. Now, what is the probability of error in matched filter? So, in case of matched filter, we can find out like optimum filter, here is also we can find out the probability of error. So, your SNR equal to S naught of t whole square divided by sigma square, which is equal to, when equal to means it is nothing but the maximum, 2 by n naught integration SI of f whole square multiplied by df. So, using Parseval's theorem, we know that SI of f whole square df, this is the integration minus infinite to infinite SI of f whole square df equal to integration minus infinite to infinite SI of t square multiply in time domain equal in square integration in square in time domain equal to integration in frequency domain, square in frequency domain. Thus, gamma maximum square equal to S naught of t whole square divided by sigma square maximum equal to 2 by n naught. Instead of SIF, I can also write SI of t whole square dt using Parseval's theorem. So, I can write 2 by n naught integration minus infinite to infinite. What is SI of t? In the previous lecture, we can see that in the optimal filter case, I can we can see that SI of t is nothing but x naught 1 of t minus x naught of 2 t. This is SI of t is x naught 1 of t minus x naught 2 of t. So, after that I can expand because this is a whole square term. So, I can expand this one as x naught of 1. So, actually this is a only square, not modulus. Okay. So, x naught 1 square of t, x naught 1 this is your x naught 2. Okay. This is your, sorry, this x naught of 2 square of t minus 2 times this is x naught 1 of t into x naught 2 times t, because x naught 1 of t minus x naught 2 limit is defined for 0 to t. This limit is already defined for a time period. Okay. That is why instead of infinite, I can write like minus infinite to capital T, that is nothing but and rest thing is same. So, gamma maximum square, that is SNR equal to 2 by n naught multiplied by, this is also one energy term E1, this is one energy term, this is x naught 2 square t. Okay. This is the energy term and this is the E2, this is E1 and minus 2 times E1 E12. This is because in multiplication form, that is why this is the energy of 1 2. So, at we can see that for different cases, if x naught 1 of t equal to x naught 2 of t implies E1 equal to E2. Okay. If x naught 1 of t equal to x naught of 2 t, that means energy of E1, energy E1 equal to energy E2, and we can say that energy E1 to equal to E1 because this is, I can say that E1 is equal to E2. Okay. I mean this signal is equal to this much. So, I can write this E12 equal to also E1. So, gamma maximum square equal to how much? 2 by n naught integration minus infinite to t x naught 1 of square t is nothing but E1, this is E1 minus 2 times E1, this is your 2E1 minus 2N, this is your cancelled out, so it is 0. So, SNR equal to 0, this condition is not possible, okay, this condition is not possible. So, another case is at x naught 1 of t equal to minus x naught of t implies E1 equal to your energy equal to E2 and U12 equal to your minus E1. So, I can write E1 E2 minus of minus 2 times E1, that is plus 2 E1 equal to 0. Okay. So, what will happen? This is this is not equal to 0, this is okay, this is not equal to 0, this was actually previous one, okay. This is not equal to, this is how much, 2 times by n naught, E1 E2, that is E2 equal to E1, so 4 times E1, okay, that means 8 times E1 divided by n naught. So, probability of error is nothing but half ERFC of s square of t divided 8 sigma square. This is the general probability of error equation. So, we know that gamma square equal to s square of t divided by sigma square. Therefore, half ERFC of how much this is, because I know gamma square equal to this much. So, I can write this s square of t divided by sigma square, that is gamma square. So, I can write gamma max square divided by 8, this is nothing but your generalized probability of error. So, I can see that this is s square of t 8 sigma, I can write gamma max square divided by 8, I can write gamma max square 8, this is 8 divided by n naught E1, okay. So, 8 divided by n naught E1 divided by your 8, okay. So, it would be probability of error would be half ERFC of E divided by this is n naught or generalized E1 yeah E, whatever this. So, in terms of energy also I can write the probability of error, and in terms of SNR also I can write the probability of error. So, this is the probability of error, this is a half ERFs of E by n naught. So, error function is a decreasing function, I have already told you, as n naught is constant, your n naught is your constant, where whenever the value of E is increased, when E is increased, the error function would decrease, okay. The error function ERFC function would decrease, and hence the probability of error also decreases. That is nothing but when your energy E is increasing, so your probability of error it would be decreasing, okay. So, I can say that like say that when gamma max square, that is SNR is increasing, your probability of error is also decreasing, okay. So, we have already seen about the match filter, what is the impulse response of the match filter, what is the probability of error in the match filter, and now finally we have calculated the generalized probability of error in the match filter, and we have seen that how this probability of error depends on your energy and SNR. So, this is all about the match filter. So, these are the books you can refer for this type of topics. So, thank you very much.